Good evening, everybody. I hope you've had a restful weekend. I thought I'd take a couple minutes to just record myself walking through the first of our exercises for the week to give you some extra idea of where to go when you're calculating moments of inertia. The first example problem we have this week is another one-dimensional rod. It's got a length L, which I believe was 10 meters, and the center of the rod, about which we're going to pivot, is at the origin, at x equals 0. Now, this particular rod is special compared to the ones we saw last week in that its mass density is non-uniform. Your rod actually gets more or less massive depending on where you are on the length of the rod. The mass per unit length function we're given, this lambda, tells us our mass per unit length goes as 3x squared plus 1, where x equals 0 at the center of the rod. When we calculate moment of inertia, we're adding up all the little bits of r squared dm integrated over the whole body that we're looking at. So in that case, we've got this rod. This function we need to put into a form that we know how to integrate. So we're adding up all these little dm's, but we want to transform this dm into some spatial element instead, so then we can integrate over the spatial variable r. Now dm is a little bit of mass. So if I go back to my picture of the rod, let's say we look at this little chunk right here. This will be a chunk dm. Now, every little chunk on the rod is another dm. dm is just one little mass element, and we're going to have to integrate over the whole rod, and that's what integrating does for us. It adds up the r squared dm for all the little bits of dm that make up the total mass of the rod. So there's our little bit of mass, and we want to write this in terms of a spatial element. So for that, we say that dm is equal to lambda times dx, where this lambda is our mass per unit length, and dx is a little tiny bit of length. How do we get a little bit of mass? Well, we multiply a little bit of length times our mass per unit length, and that will give us the little chunk dm. Our dm is associated with this differential length element dx. You have a length dx and a mass dm that goes with it. If the rod were uniformly distributed, the density function would just be the total mass of the rod divided by the total length. In our case, however, the rod is not uniformly distributed, but we have an explicit function for how the mass varies with the length. We know the mass density per unit length is 3x squared plus 1. So now we put this differential mass element back into our integral. Our moment of inertia integral is now the integral over the body of the rod of r squared times 3x squared plus 1 dx. So we've got our dm, the differential mass element, in terms of the differential length element dx instead. So our next step is to make this r more specific to the problem. R, in general, measures the distance from your axis of rotation to the mass element dm. So for the mass element dm I drew on my picture, the associated r would be what I have drawn right here in red. That's my R. We notice, since this problem is a one-dimensional problem, R measures up and down the rod, R is equivalently X. Our distances are all measured along the x-axis out from x equals 0. So when we're looking for r squared, what we've really got is x squared. And the last thing we can do with our integral is, all right, we're integrating across the entire body of the rod, which is simple in this case because the rod is one-dimensional. So if we want to hit all the mass, all the length elements on the whole rod, we're going from x equals negative L halves at the left end of the rod out to x equals positive L halves at the right end of the rod. So we started with our general form for the moment of inertia integral, and we wind up with an integral where everything is in terms of x and the limits of the rod in the problem. So now we've got something that we can actually integrate and find the moment of inertia for the rod. You could do the same thing in 2 or 3 dimensions if you wanted. It would just be a little bit trickier. For the actual integrals you carry out in this case, we'll mostly be sticking to one-dimensional problems like this. I hope you found this useful. You can go ahead and try the rest of the problem now. If you have any trouble, I'll see you in the small groups. And I'll continue posting these as we go ahead. I think I'll do the first problem or 2 for each day, just do a little bit of it, kind of show you how to get started. Yep, hope it's been useful. Have a good night, and I will see you Monday.